I see that we have people joining already, so I'll go ahead and get started. I hope you all have had a good week so far, getting through everything and getting back into the swing of things with our classes. Today we're going to start covering Chapter 7, the first chapter that we'll work on here. We'll just go through in order, Chapter 7, 8, 9, 10. So for Chapter 7, we're actually working on a lot of ideas associated with geometry, at least during the first half of Chapter 7. Basically, we're finding things like area and volume of figures that are not what we would call regular figures. That would be non-polygonal or non-polyhedral figures. If it would be a little more specific. Basically, there's not necessarily going to be a lot of straight lines here, but we still want to be able to find the area and the volume of these different shapes. And so that's our early focus in this chapter. The later half of the chapter is more on the applications of calculus, as far as how they would apply to things like engineering and physics and related things. So we'll focus on those after we get through this early stuff, of course. So section 7.1, we'll start with that today. I will be able to finish 7.1 today and probably get started on 7.2 also. At least part of 7.2 today. And we'll get through that and keep going from there. I mentioned I would get a calendar ready for the semester. Again, I want to have that ready by tomorrow, hopefully. So I will make sure I upload that and let you all know via an announcement when that's ready. Okay, so starting off looking at the area between two curves, the idea here is that we have some region. Maybe we have one function f of x that forms one boundary, and we have a second function g of x, maybe that's the another boundary. And we have two lines here. This is A and B, and these all perfectly enclose this region that I'm shading. And so we're trying to find the area of that shaded region. Okay, and this is actually pretty straightforward. Our area, in this case, is equal to the integral from a to b, because we know here's our limits of integration right here. This is our lower edge, and here's our upper edge. And so one thing that we know from Calculus 1 is that the area beneath a curve is the integral. So we have the area beneath f of x, which is this whole area, these two parts. And then we have the area beneath g of x, which is this part, this integral. So if we were to integrate f of x, we'd get both of these sections together. And if we were to integrate g of x, we would get this section. So if we have both of these, and we also have this one by itself, the way that we can solve for the shaded region is to take the area underneath f of x and subtract the area that's underneath g of x, and that leaves what is in between the two. So our formula here is the integral from a to b of f of x minus g of x dx. And we tend to designate f of x as the top function, the furthermost from the axis, and g of x is the bottom function, the one closest to the axis, or to the x-axis in this case. And so that's our basic concept of an area between two curves. Now, depending on the problem, sometimes we'll have to find the limits of integration ourselves. Other times they will be provided to us, and we'll talk about that as we go through some examples. But before we go through some examples, let me talk about some other possibilities here. So it could be that we have a pair of functions now. Instead of being written as functions of x, it could be that we have functions of y. So here's f of y. We'll call this line g of y. And now we have horizontal lines c and d, and that will enclose this area. So in this case, when we're looking at functions of y instead of functions of x, then we'll go ahead and use our y variables instead of our x variables. So the idea is that because these lines are curved in some cases, we have a straight line here, but this edge is curved, we can't use that. I mean, this is not a vertical line either. We can't use those as limits of integration. Our limits always have to be constant values. So we'll integrate from c to d, and we'll end up taking f of y minus g of y dy. And again, looking at the y-axis as our focus, the function furthest from the y-axis, f of y, is first, and the closest to the y-axis is g of y is second. And it's the same principle that's being applied here. We just rotated the picture 90 degrees. Alright. Now, another situation which may arise what happens if let me see, we have a curve f of x and we have another line or curve g of x, and what the integral, or we want the area from a to b, but we look at this area between the two, and there's actually a point in between. We can identify that as c, where the two functions intersect and they actually cross. So what we're saying is between the points a and c, the curve that forms the upper boundary is actually f of x, and g of x forms the lower boundary. But between c and b, they've switched, and now g of x is our upper boundary, and f of x is the lower boundary. So in this situation where they cross at some point between the endpoints, we'll call that point C just for convenience sake. When we set up our area formula for this, we have the integral from a to c of f of x minus g of x dx plus the integral from c to b of g of x minus f of x. Okay, so the issue is that the lines do cross here. Now, if we were to integrate from a to b, in this case, if we didn't do the second integral here, we just integrated a to b f of x minus gx. What would happen is where f of x is on top of g of x, if we subtract them, we'll get a positive value for that area. But if g of x is actually above f of x, like it is here, then integrating f of x minus g of x would be a negative number. So we'd get a positive area and a negative area, and they wouldn't necessarily cancel out. It just depends on the relative size of the areas, but we wouldn't get the correct number by any means. We would get a positive number and a negative number, so whichever one was larger would tell us how the answer would appear. And this part looks a little bit bigger in this case, so we'd probably get a negative answer if we integrated from a to b. Alright. So that's our kind of our main formulas that we utilize here. And the guiding principle is that we want the whichever variable we're using, x or y, as our what we call our independent variable, x or y or x like we have here. We want the furthest one from that axis, from the x-axis, furthest one minus the closest one. And if they switch, we'll have to switch those as well when we write them down. Again, furthest one minus the closest one. Okay. Let's look at some examples utilizing these concepts. So we're looking on page 450. And so let's start with problem 6. Now, so we're given a pair of functions. We have y1, or I guess technically they're equations. y1 equals x squared plus 2x plus 1, and y2 is equal to 2x plus 5. So, first thing we want to do is graph these two equations. Now, 2x plus 5, we're probably more comfortable graphing that than the parabola. But if we happen to notice that the parabola is x plus 1 squared, since that's how x plus 1 squared is multiplied out to x squared plus 2x plus 1, that means that we have a horizontal shift of -1, so the parabola would actually just start right here, y-intercept of 1, so it would look something like this. Now, the line 2x plus 5 has a y-intercept of 5 and a slope of 2. Oops. There. Something like that. Now, the graph doesn't have to be perfect by any means. We just want an idea of which function is the top function, which function is kind of the bottom function in regards to where our shaded region is located. Now, here's y2 forming the top boundary and y1 forming the bottom boundary, because we have our line is the top edge here, and then our parabola is the bottom edge. Alright, so we have our graph, and this graph is also shown in your book as well, if you have any questions about that. And now the question is, how would we set up an integral to help us find this area? Well, before we can set up our integration, we need to figure out what points these 2 points of intersection are located at. Now, since this is where the 2 equations cross each other, here and here, that is actually where the 2 equations are equal to each other. So if we want to find the points of intersection, we'll go ahead and set y1 equal to y2. So y1 is x squared plus 2x plus 1. y2 is 2x plus 5. So we set those equations equal to each other, and we need to solve for x, basically. So we'll subtract over the 2x and the 5, and so that gives us x squared minus 4 is equal to 0. Okay. And we can factor and solve that, or if you want to move the 4 over and just take the square root, that works also. But what we end up with is x minus 2 and x plus 2. So we get x equals 2 is one point of intersection, and x equals negative 2 is the other. So this is a negative 2, and this is a positive 2 right here. Now, I haven't drawn a great graph, as you can imagine. Probably better than I would have put on a board vertically. But we don't always want to just look at the graph and trust our eyes, because there could be some distortion to the image as far as how we've sketched it and how we've set it up on our paper. That's why it's important that we go through and actually solve for the points of intersection. We make sure we get the correct values. So not only are these going to be the points of intersection, this will be the limits of integration. And that's really what we're trying to find here, is what limits are we going to use for this integration. Okay. So let's set up our area then. We know it's an integral from negative 2 to 2. Now, we said before we want the top function first minus the bottom function second. And we already identified y2 as the top function, so we'll put y2 first down here. So that'll be 2x plus 5. And from that, we want to subtract y1, which is x squared plus 2x plus 1. So we can go ahead and subtract those. We're just subtracting polynomials, so the main thing here is make sure we get the signs right, because if we don't, that's going to give us the wrong answer, of course. But we'll end up with 4 minus x squared dx. And now we can complete our integration and plug in our limits after that. So integrating these terms, integral of 4, anytime we integrate a constant, is just going to be the constant times x, so 4x. And we have x raised to the second power. In that integral, remember it's a power rule, we add 1 to the exponent, so x to the third, and then divide by the new exponent, so x3 over 3. Now at this point, we want to go ahead and plug in the limits of integration so we can go ahead and calculate the area. Now, this particular problem in the book only asks you to set up the integral but not to actually solve it. But I think it'll be good just to go ahead and go through and complete that, make sure we're okay with that concept. So we're going to take 4x minus x cubed over 3 and plug in the 2 first. So x equals 2 first. 4 times 2 is 8. Minus. And then 2 to the third power is 8 over 3. And then we'll subtract and we'll plug in the bottom limit or lower limit of integration, which is negative 2. So 4 times negative 2 is negative 8 minus, and this will be negative 2 to the third power, which is negative 8 over 3. That out of the way. And so we end up with area equals 8 minus 8 thirds minus parentheses negative 8 minus a negative 8 thirds. Now, we know these two negatives will make a positive, and if we distribute this minus sign, then we'll get 8 minus 8 thirds plus 8 minus 8 thirds. Now from here we'll just combine our like terms. 8 and 8 is 16, minus 8 thirds minus 8 thirds minus 16 thirds. And from there we can just, if we want to, we can leave it as an improper fraction, or we can convert it to a mixed number if we like. 3 times 16 is 48, minus 16 is 32, so 32 over 3. Okay. Does anyone have any questions so far? Okay. Let's look at another problem. Let's go ahead and look at 16. Okay. Sorry about that. So we get y equals negative x squared plus 2, y equals x minus 3, and we're given the additional boundaries of negative 1 and positive 1 for x. So negative x squared plus 2, it means we go up 2, and we draw a x squared graph, parabola, going down. And then x minus 3 means it has an intercept of negative 3, but a just a slope of 1. That's not perfect, but it's good enough. So yeah, we end up with, well, we have this area between the two curves, but we also keep in mind they've also provided values for x. So we'll use x as negative 1 and x is positive 1 as boundaries. And so there's the region that we're looking at. Now, even though part of the graph is below the x-axis, the approach that we took with the first problem is still the same approach that we use here. We need to figure out which of the functions forms this top boundary. This is the quadratic one, so that's y equals negative x squared plus 2. And then our line, y equals x minus 3, forms the bottom boundary, but we're only looking at the area from -1 to 1 based on the information provided. And we see that these two, the line and the parabola, actually meet at two different places, but it turns out we're not interested in what those two numbers are because they've actually provided the limits that they want us to use here. And so that's really something we want to keep in mind, is that it's not always the area between the two curves, it's also the area between the boundaries provided. These are not always given to us, as we saw from the first example, but if they are, we have to keep track of that. So we know our integral is going to be from -1 to 1. Our top function, or curve, is -x squared plus 2 minus our line, which is x minus 3. Those are subtracted from each other. And we have dx still. So if we go ahead and subtract those two binomials, we get -x squared minus x plus, it looks like 5. Yeah, 2 minus -3. And that's probably why they didn't ask us to find the area between the two curves, because this is not factorable, so it wouldn't be easy to find those points where they intersect. Anyhow, that's the equation that we're given. Now we can go ahead and complete the integration, and then complete the definite integral where we plug in the limits of integration. So in our integration, -x squared, we add 1 to the exponent, so -x to the third over 3. -x, remember -x technically has an exponent of 1, so it's -x to the second after we add 1, and then divide by 2, and then plus 5x, because our constant is always a constant times x when we integrate. Okay. So there's our integral, and now we want to go ahead and plug in our x equals 1 and our x equals -1. So for x equals 1, we end up with -1 over 3 minus 1 over 2, and plus 5 times 1 is 5. And then we plug in x equals -1. Now, here we have to be sure we keep our signs straight, because it's easy to make a little mistake here. -1 cubed is -1 times the negative outside of that makes it positive 1 over 3. -1 squared is 1 over 2, and that's subtracted still. And 5 times -1 is -5. And again, from here, it's really a matter of simplifying. You combine our like terms and figuring out what we have. So we have -1/3 minus 1/2 plus 5 minus 1/3 plus 1/2 plus 5. So one thing that we notice at this point is that we have a -1/2 and we have a positive 1/2. Those are just going to cancel each other out. So we have the 5's, which is 10, and then the two -1/3, which is -2/3. So 10 minus 2/3, which gives us 28 over 3. 3 times 10 is 30, minus 2 is 28 over 3. Okay. Now, whenever we write down our answers, you see I wrote it as 28 over 3. We could write it as 9 1/3, potentially. But unless it's an actual application problem where the answer makes more sense to be in a mixed format versus just an improper fraction like we have here, it's okay if we leave it just like this. Now, if we're trying to find the amount of work done by applying a variable force for over this distance, and we come up with an answer of 28 over 3 Newton meters or joules, we wouldn't really say 28 over 3 joules. We'll say 9.3 repeating joules, or 9 1/3 joules. I mean, in cases where there's units of measurement present, we can go ahead and make that a mixed number. Otherwise, we can just leave it as a fraction, or improper fraction. Okay. We'll look at 24 next. Okay. Now this time both functions have been given to us as a function of y. And it seems a little more scary than if we had functions of x's, but we should be able to manage. So now, first of all, the line g of y equals negative y. If we have x equals negative y, then that's basically identical to y equals negative x, which is just our negative diagonal line right there. Now, this one, if we were to multiply it out, it would be 2y minus y squared. So it is a quadratic, but by giving us the factored form, we could say one intercept is y equals 0, the other intercept is y equals 2, so we can fill that in. And then we know that the vertex is halfway between the two intercepts, so the vertex would be at y equals 1. And if we were to plug in y equals 1, 1 times 2 minus 1, 1 times 1 is 1. So we'd end up with a parabola such as this. And now we can identify the shaded region that we're trying to find the area of. Now, again, this time we haven't been given limits of integration like we were in the last problem. So we need to set the two functions equal to each other in order to solve for these limits of integration. So if we take negative y equals y times 2 minus y, okay, what I'm going to do is I'm going to take everything here and move it over to the left hand side. That way the y squared term will be positive. So we'll end up with y squared, and this will be a minus 3y equals 0. And so we can factor out the y again and say y minus 3 is our other factor, So that gives us y equals 0 and y equals 3 as our limits of integration, or points of intersection. Either way. Alright, so we can already tell that 0 was a point of intersection. We had that labeled on the graph to begin with. But this point down here where these two pieces intersect turns out to be 3, where that happens. Which graphically it does make sense, which is nice. Alright, so we set up our area. Now, because we're working with functions of y, we want the function, when we decide on the order of functions, well, first of all, we know we're integrating from 0 to 3, so we'll write that down first. But again, when we have x, we know we go top minus bottom, but with functions of y, we'll go right minus left. So on our right side, we have our parabolic curve, which is f of y, and that means we'll have y times 2 minus y, and from that we'll subtract the line on the left, which in this case is negative y. Alright. So we'll multiply this out before we try to combine the like terms. So we have 2y minus y squared, and then this will be a plus y once we resolve the two negatives. So putting that together gives us 3y minus y squared dy. So we have to be, and we don't see this as often where we work with functions of y instead of functions of x. Probably 99% of the time we'll be working with x's instead of y's, but in this other 1 or whatever percent of cases, it's nice to be able to change our point of view and work with the y values as well. That flexibility is important. From here we can integrate. Now again, this is 3y to the first power, and so when we integrate that, it'll be 3y squared over 2. Y squared, we add 1, so it's y cubed over 3. And we go from 0 to 3. Now, one of the things about this particular integral, so we see the bottom limit of integration is 0. And what happens when we plug 0 in is it makes this one 0 and it makes that one 0. So really we only need to plug into 3 in this case. It's not that we'll never have to plug in 0, it just depends on the formula inside. But in this case it does give us a pair of zeros when we plug that in. So for plugging in 3, first of all, 3 squared is 9 times 3, 27 over 2. Plug in 3 here, 3 cubed is 27, divided by 3 is 9. Okay, so we basically end up with 27 over 2 minus 9. So this would be 27 minus, and this 2 times 9 is 18. So 27 minus 18 is 9 over 2. And so that will be the area of that particular figure. Okay. Next, I want us to look at number 38. In 38, we're given f of x equals sine x, and g of x is equal to cosine of 2x, and we're also given boundaries for x, which is negative pi over 2 less than or equal to x less than or equal to pi over 6. Now, for these two functions, we see they're a little bit different trig functions. They have different angles inside. Sine is a function of x and f of x, but cosine is a function of 2x in g of x. So because they have different angles, we know the shapes will be, we know the shapes for sine and cosine are similar, but with cosine 2x, we know multiplying by 2 inside will actually shrink the graph horizontally and make it have a shorter period, basically. And so, one of the things I recommend when it comes time to graph this, especially when we're given limits like this, which is nice, I would suggest we set up just a basic chart where we can just fill in some values just so we know what each of these are doing. Now our lowest point we have to worry about is negative pi over 2. I'm going to go ahead and throw in negative pi over 4 and 0, and then our top limit is pi over 6. So I wanted to put a few more points in between so we can kind of get a better idea of what the graph looks like between these two endpoints. So we will evaluate sine of negative pi over 2, and then that is negative 1. Sine of negative pi over 4 is negative square root 2 over 2. Sine of 0 is 0. And sine of pi over 6 is 1/2. Then doing the same thing for cosine 2x, if we plug in negative pi over 2, 2 times that would be negative pi, and cosine of negative pi is negative 1. Plug in negative pi over 4, 2 times negative pi over 4 is negative pi over 2, and so cosine of negative pi over 2 is 0. Plug in 0, cosine of 0 is 1. And plug in pi over 6, and cosine 2 times that's pi over 3. Cosine of pi over 3 is 1/2. So it looks like these actually start and end at the same points. So these are points of intersection for these two graphs, but they have different values in between. Okay, so both graphs start at negative 1. Now sine of x at negative pi over 4 has a value of negative square root 2 over 2, which is about negative 0.7. We'll kind of eyeball where that is. Goes through 0, 0, and at pi over 6 it has a value of 1/2. Okay, so we don't necessarily get a great idea of the curvature of sine in there, because between negative pi over 4 and pi over 6, it's actually almost a straight line. Not quite a straight line, but it's relatively close to y equals x, at least between negative pi over 12 and positive pi over 12. We don't have to worry about that. But then we look at the other graph, cosine of 2x. We have a coordinate of negative pi over 2, negative 1, which is here. Negative pi over 4, comma 0. 0, comma 1. And pi over 6, comma 1/2. So we come back here. Okay, and so we know this is cosine of 2x, and we know this is sine of x. I didn't draw a great sine graph there, to be honest. Now we can see there's our shaded region between the two curves. And we can tell that cosine 2x is the top function and sine x is the bottom function. So setting up our area, we know it's the integral, negative pi over 2 to pi over 6. And we're going to take our top function, cosine 2x, minus our bottom function, sine x, and integrate with respect to x. So that's how we set up that integral. What is the integral of cosine of 2x? Does anyone have that? We kind of talked about that last time, but I want to see how well you remember that. Sine 2x, yeah? There's one other thing missing from that, though. We know the integral of cosine is sine, but because the angle is 2x, there's something else that is also included. Not negative, it is positive, that was correct. So we know it's sine 2x, but because the angle inside is 2, we know it's going to be a 1/2. Now, we're not going to include a square because it's not a power rule. But the idea is that normally we would do a u substitution for 2x, u equals 2x. We get a derivative of 2. And that 2 would then turn into a 1/2 when we resubstitute it into that integral. And so it ends up being 1/2 sine of 2x. This is one that shortcut we were talking about before, where we can do it with the u substitution, but we want to learn the pattern that leads to being able to just look at that term and understand what the integral is. Okay. So again, keep working on that concept. What about the integral of negative sine? Yeah, we'll have two negatives, which effectively makes it a positive. That's correct. And it is cosine. I'm curious where you got 1/2 out of that. If it's just sine or cosine, then we know the integral is sine or cosine, or the opposite. The only question we really have to worry about is it positive or negative. And this one does end up being cosine x. Unlike our power rules, we don't have to add 1 to the exponent and then divide. Right, exactly. So that's what we have to be careful not to mix up here. Okay. So yes, that's our integration, and now we can go ahead and plug in our limits. So our top limit is pi over 6. We'll do that one first. 2 times pi over 6 is pi over 3. Sine of pi over 3 is square root of 3 over 2 times 1/2 would be square root of 3 over 4. Yeah. And then cosine of pi over 6 is square root of 3 over 2. If we plug in negative pi over 2, 2 times negative pi over 2 is negative pi, and sine of negative pi is 0, so 1/2 of that is still 0. Cosine of negative pi over 2, also 0. Okay, and so our area is just root 3 over 4 plus root 3 over 2. And we'll make that 3 root 3 over 4. Okay. Yeah, whenever we have our trig functions, especially if we're finding like an area between, as we are in this case, it does make it a little more difficult because, one, the graph ends up being a little bit more tricky, and so that's why I recommend making a chart of values, and not just the endpoints, but a couple of points in between, so we can get a little bit more definition to what the graph actually looks like, and it also helps us discern which graph is above the other. And then beyond that, the graph doesn't have to be perfect. We just have to have an idea of what's going on. So we know that cosine 2x was the top function, sine x was the bottom function, and that allowed us to set up our integration here from the one endpoint to the other. We completed our integration, plug in our limits, and simplify our answer from there. Right. With trig functions like sine and cosine, we know that the integrals are either cosine or sine. It doesn't become sine squared or cosine squared. Yeah. It's only with like x raised to a power where we have to concern ourselves with that. Yeah. I don't know, that might be all I wanted to do here. Let's see. Yeah, that's all I wanted to do here. Okay. All right. So let's move on to section 7.2. Section 7.2 is on what we call, it's about talking about volumes of objects, and specifically we're looking at the disk method. Now, so when we look at volumes now, we end up looking at volume problems both in Calculus 2 and in Calculus 3. However, we don't have all the tools in Calculus 2 that eventually we'll have in Calculus 3 to work with, because we haven't learned them yet. So the ones that we look at will be a little bit different here than you might see in the next course. When we talk about we're going to talk about volumes of revolution, or yeah, that's a good way to say it. Now, a volume of revolution is when we revolve a graph around one axis, and it doesn't have to be like the x-axis or the y-axis necessarily. It could just be revolved around a line x equals 2, for instance. So the axis of revolution could be any line in any direction, basically. It does have to be horizontal or vertical, otherwise we can't really address it. But a volume of revolution, so we revolve a function about a horizontal or vertical axis. So this is, let's think of a relatively simple example. We just have a line, and we're going to revolve that around the x-axis. Okay? And so generally it's not just a line, but a shaded region, in this case bounded by the line in the axis, and we have this other line on the right hand side. So essentially we have a triangle in the xy plane. And we're going to revolve this around the x-axis. So that means this line is going to, if we imagine the third dimension kind of coming out from the page, this line is going to revolve around that x-axis and create a 3D figure. Okay. So here's our original line, or triangle, once again, but we're going to revolve that and create what is basically a cone. Now what I've done is I've drawn a third axis here, which kind of comes out from the page, but it's hard to draw that when it's coming out from the page, so we kind of draw it at an angle. And so here's kind of a view of the bottom of this figure. But the idea is that we take this triangle and revolve it around an axis, and it creates this cone shape. Now, in this case, this is a volume of revolution. And this is one of the types of problems where we're interested in figuring out what is its volume. Now, the area of a triangle and then the volume of a cone, these are things that are well established in geometry that we have formulas for already. The area, the volume of a cone is 1/3 pi r squared h. So we take 1/3 times pi times the radius squared times the height. So it's actually pretty straightforward to do this from a geometric standpoint. What we're interested in, for example, if we have a function such as f of x equals x squared from 0 less than x less than or equal to, let's say, 2, we know the graph of x squared is a parabola. We only need to worry about the right half because we're only going from 0 to 2. And so normally we would also say y equals 0 is also a boundary here so that we can enclose the shaded region completely. And we want to revolve that around the x-axis. Now, as far as what that looks like, if we try to sketch it in 3 dimensions, we have our parabolic curve here, and that's going to be reflected down. So we get a kind of a mirror image on the bottom half, and this will be a circular image on the side. And so it's not a great picture, unfortunately, but the idea is we've taken this and revolved it around the axis and created a 3D shape. Now, let's look at how the disk method figures into this. How can we utilize a disk method to find the actual volume here? Well, the idea is, at least with integrals in general, is that the concept of an integral, which we talked about in Calculus 1, where we do like Riemann sums and such, is that instead of a smooth figure, we have just a bunch of little figures that are added together to equal the total area overall. So if we were to chop this up into different pieces, into like horizontal parallel pieces, just take a bunch of vertical slices through the figure, so we have this shape, and what we're going to do is cut it into different slices. So that's a better drawing than that one. It's less busy. Anyway, so we're going to have like a dot here at the end. We're going to have a circle here. We're going to have another circle here. And the circles are going to get larger and larger until we get to the end. So it's really just a bunch of circles stacked together that are creating this figure. And the circles, because they're filled in, they actually are called disks. That's the kind of geometric name for the figure. A circle is actually just the outer boundary. A disk has the middle filled in as well. Alright, so the question is, how do we get the area of each of these circles that make up, this entire figure? Theoretically, there's infinite circles here that we've basically got stacked together, but they exist between 0 and 2, based on what we're given. So we think about each of these circles that are stacked together. We have a little circle here, and we have a much larger circle here. But what changes from one to the next is the radius of each of these circles that are being created. The radius of each of these disks. And so at 0, since it's just a point right there, the radius ends up being 0. So we just have a single point at one side. But the further that we go, the larger the circle that we get, and the larger that the radius is, in a corresponding manner. And so we look at each of these circles, and we know the area, or the area of a disk, is pi r squared, which I've written off the screen. Sorry. So the area of a disk is pi r squared, and that's kind of our traditional formula that we understand is associated with a circle or disk. But the issue is that the radius here is different for each of these circles now, because the circles over here have a very small radius, relative to the axis of revolution, versus a much larger radius the further out that we go. So we have all these circles stacked together of different sizes. And so in order to add all those volumes together, or all those areas together, that's how we're going to represent it as a sum. Now, rather than represent it as an actual Riemann sum like we would have talked about in Calculus 1, I'm going to go ahead and make the transition to a definite integral, which is the correlation that we proved in Cal 1. And the idea is that we take the area for each of these disks and add them together, and that's equivalent to the volume. And so volume using the disk method, let's go ahead and look at this formula. Now this is a general formula. We think of it as the sum of all of the circles from point A to point B. The areas of each circle is pi r squared, and we add all those together. That's why we've turned it into a definite integral. We also include dx, which is basically the thickness of each circle horizontally. Now, the idea is that these are all infinitesimally small, so dx is negligible. And so ultimately we end up with pi r squared being integrated. Dx is just there to indicate that that's our main variable. Now we come back to our function here, f of x equals x squared, and the distance here between the axis of revolution and the function, this is the radius. This tells us when we revolve this part of the graph around the axis, it tells us how large of a circle is going to be created. So closer to 0, it's going to have a smaller circle. Further from 0, we'll have a much larger circle based on that radius. But the radius, in this case, radius equals the distance from the function, in this case f of x, to the axis of revolution. And so, for our particular example, which uses, and let me write this down again, f of x equals x squared, y equals 0, and then 0 less than or equal to x less than or equal to 2. Here's our shaded figure once again. And we're revolving about the x-axis. So our volume in this case, our limits will be 0 to 2, because it starts at 0 and goes to 2. We have pi, of course, that has to be present, because anytime we work with areas of circles, we have pi. Now radius, we said, was the distance from the function to the axis of revolution. Now our function is just x squared, and our axis is right here on the x-axis, which is 0, y equals 0. So r is the distance between x squared, or y equals x squared, and y equals 0. So essentially, r is equal to x squared. Probably the easiest way to calculate r, though, is to subtract the two pieces, the function and where the axis is located. So the x-axis is also the same as the linear equation y equals 0, so we can utilize that. Now, that's our radius. Now, our radius has to be squared. We don't want to forget that, especially in this problem. So we said, further up, volume is integral a to b pi r squared dx. So we do 0 to 2 pi. Here's r squared dx. So whichever expression we get here, we still have to square it before we go about the rest of the problem. So that means that volume will be integral 0 to 2. Now, we have the pi value here. Probably it's going to be easier to work with if we factor that outside the integral. Pi is a constant, so we can freely move constants in and out of the integral as necessary. X squared squared will be x to the 4 dx. 0 looks out of place. And if we go ahead and do our integration, again, x to the 4th, we add 1 to the exponent and then divide, so it would be x to the 5 over 5, and that's from 0 to 2. We plug in our 2, and so we get pi times 32 over 5. Plug in 0 gives us 0, so our volume is just 32 pi over 5. And we see this in this type of problem pretty commonly. The hardest part of the problem is just setting it up in the first place, getting the correct limits, getting the correct function inside. The actual execution of the integral is pretty straightforward. It's just a nice polynomial term that we have to integrate. Occasionally we might get something a little more involved. We might have like a 1 over x curve, for instance, but even then it's not terrible. It would require a little bit more work. Okay. Let's look at some more of these examples. I know we've barely got started with this, but there's a lot to take in. Let's say we have the line y equals 2x plus 1 with boundaries x equals 0, x equals 2, and y equals 0. Let's go ahead and say y equals negative 1 is the lower boundary. And we want to revolve this about y equals negative 1. Now, in this case, we have linear functions for everything, so it's relatively easy to graph. At x equals 0, 2 times 0 plus 1 is 1. And at x equals 2, 2 times 2 plus 1 is 5. So here's our line. We said y equals 1, negative 1, sorry, is our lower boundary. And we connect those with x equals 2 and x equals 0. And we end up with a trapezoid shape. Now we want to revolve this around the y equals negative 1 line. And so what's going to happen is we're going to revolve this around, and it's going to be like a kind of a 3D trapezoid kind of thing, where it has a circular base, a circular top, and the slanted sides. The technical name would be like the frustrum of a cone, but we don't have to worry about that. There is actually a formula for this shape, so it's not like we're doing anything new here, but we're looking at it from a calculus standpoint. Okay. Now, the one thing we always want to figure out is what is the radius function. Now, the radius is kind of the vertical component here from the top edge to the axis of revolution. So that's our radius right there. And so we go back to what we talked about before, where to find the radius, r of x, we take f of x minus the axis of revolution. So in this case, r of x, our radius function, is our top boundary, which is 2x plus 1, minus our lower boundary, which is at negative 1. So we're actually subtracting a negative 1 here, which means we end up with 2x plus 2 when we simplify everything together. So now that gives us our radius function. From there, we can go ahead and set up our integration for the volume. Again, volume is pi times r of x squared dx from a to b. A and b are just the left and right endpoints, which are given in the problem 0 and 2. I'm going to go ahead and factor out the pi. And then r of x is 2x plus 2 binomial that is being squared. Okay, so we want to make sure that we get r of x correct, because if this is incorrect, then everything else that follows is going to be incorrect. But I mean, we know how that goes. So our next task is we probably should go ahead and multiply out this product, 2x plus 2 in parentheses squared. So we can take that binomial and FOIL it times itself. This is going to give us 4x squared plus 8x plus 4 dx once we square that. And now we're at a point where we can integrate and then eventually substitute in our limits of integration. What is the integral of 4x squared? Someone go ahead and put that in chat. 4x to the third over 3, right? Eight x, we approach the same way. That's x to the first power. So it's 8x squared over 2. So just 4x squared. So if we're going to divide by 2, 8 over 2, we can just write down a 4 there and make it a little bit easier. What about the integral of 4? What would that be? $4x. Good. Okay, and from there it's just a matter of plugging in our limits. Plug in 2. 2 to the third power is 8. Times 4 is 32. Divide by 3. 2 squared is 4. Times 4 is 16. And 4 times 2 is 8. Now if you plug in 0, that just makes all three of the values 0, so we can effectively ignore it. But we look at what we have left over here, 32 thirds plus 24. So that'll be 3 times 24 is 72, plus 32 is 104 over 3. Is that right? 72 and 32 is 104, yeah. (104 pi over 3). Okay. Let's go ahead and look at one more example here with a disk method. Let's look at this one. This is actually from our textbook, page 461, 16b. Actually, no, I don't want to do that one. I'm sorry. It's not quite where we're at just yet. I'll just make up another problem. Let's say we have f of x is x squared plus 3. We have y equals 2 as a boundary. We also have x equals -1 and x equals 2 as our other boundaries. And we want to revolve about y equals 2. Okay. So, x squared plus 3, this is a parabola that's been moved up 3 places. a great looking parabola, but there we go. We have y equals 2 as another boundary right here. X equals -1 and x equals 2. And so that is going to enclose this particular shape. Alright, and we're going to revolve that around this line y equals 2. Okay. So my question to all of you first is, what is r of x going to be in this particular problem? Remember, we said r of x is the distance from the function to the axis of revolution. So here's our radius, basically our vertical component between our curve and our axis. Okay. Well, our function is x squared plus 3. That's this top curve right here. Our axis is y equals 2, because we know that we're revolving around y equals 2. And so putting that together, x squared plus 3 minus 2, that's going to give us our radius function of x squared plus 1. Okay. And that right there is probably the most difficult part of this type of problem, is correctly identifying what the radius function is. That's really the only piece that we're missing once we get the graph. Is we have our limits of integration. We know it's going to be -1 to 2. We know we're going to have pi r squared dx inside the integral. And so the only question is, what is r of x? What is r? A radius function, and this is our calculation now. So our volume is pi times our integral -1 to 2, and we have r of x squared, which is x squared plus 1 squared dx. So again, pi r squared. We'll make sure we square this polynomial. So we'll go ahead and square that before we integrate. That'll be x to the 4th plus 2x squared plus 1. Yes, for the disk method, we're just taking the function minus the axis. Technically speaking, if their positions were switched, like if the axis was above the function, we would take axis minus function in that regard. It's actually the same principle that we looked at in the area between two curves, is that we always take the top thing minus the bottom thing, and that's really what it boils down to. In this case, since the function is kind of the top boundary and the axis is the bottom boundary, that's the order that we subtract them in. But if they had been switched, then we would go the other way. We take the axis minus the function. So it's not literally always function minus axis. It also depends on orientation, which one is above the other. hopefully that helps. So at this point we can go ahead and complete our integration. So x to the 4 becomes x to the 5 over 5. 2x squared becomes 2x to the 3rd over 3. And 1 just becomes x. Now this time we have two non-zero limits, so we'll have to make sure we plug in both of these numbers and combine all of our like terms together and so on when we calculate this outcome. So plugging in x equals 2 first gives us 32 over 5. 2 to the 3rd power is 8 times 2 is 16 over 3. And 2. Then for x equals negative 1 to the 5th is negative 1 over 5. Negative 1 cubed is negative 1 times 2 is negative 2 over 3. And minus 1. Again, the making sure we get the signs right is probably the only concern at this point. So we have 32 over 5 plus 16 over 3 plus 2 plus 1/5 plus 2/3 and plus 1. So adding our fifths together, that's 33 over 5. 16 over 3 plus 2 over 3 is 18 over 3. 18 over 3 is just 6, and then 2 and 1 makes 2, 3. So 9 plus 33 over 5. So that'll be 5 times 9 is 45 plus 33 is 78 pi over 5. Okay. Are there any questions on that? So that's the first half of section 2. The other half will be on what's called the washer method, which is basically two disk methods put together. So it's not a huge stretch, but I wanted to make sure we're okay with this topic first before we continue on to the next one. Let me go ahead and write down some homework problems for y'all. So from section 7.1, let's see. There we go. This is on page 450. Go ahead and look at number 7. 17, 23, 37, and 39. And on section 7.2, this is page 461. There, we can go ahead and look at number 5. Just go ahead and look at 5 and 6 there. There's some other problems that we could work, but I want to make sure you're okay with the basics there first before we dive into some of the other problems. So none of those have strange axes or anything like that. They're just the function as the radius. Again, these are not to be turned in. It's not for a grade, but I do hope that you look at each of these examples or these problems I've assigned and try to work through them. And again, let me know if you do have any questions. I can either point you in the right direction or go ahead and make a video about how to work through some of the different specifics of the problem. So anyway, I think that's all we're going to do for today. So we'll leave it at that, and I do hope you all have a good weekend, a good rest of the day, and y'all take care, and we'll continue with this on Tuesday. See you later. Take care, all.